I'm going to talk about bio-inspired celestial compass yields new opportunities for urban localization. This study is written by Julien DUPEYROUX, Stephane VIOLLET, and Julien Serres from the Institute of Movement Sciences, Marseille, France. Desert ants are known to robustly estimate their position from their nest while foraging for food, which is a great source of inspiration to design navigation strategies working without GPS or any global navigation satellite system (GNSS). In this study, we introduce the Antbot celestial compass mounted on board a car for heading detection. Antbot is a hexapod robot fitted with ant-like visual sensors. One of them is a celestial compass working in the UV range, comprising only 2 pixels to detect the state of polarization of the skylight. This compass provides an optical heading while navigating outdoors with excellent performances regardless of environmental conditions. By rotating a pair of polarized filters above the 2 pixels, we can scan and access the state of polarization of the sky, then provide a reliable optical heading. Could the onboard celestial compass use for automotive applications? The celestial compass was mounted on board a car to test the optical heading estimations over a long distance instead of thousands of meters achieved by the onboard robot. The onboard celestial compass is composed of 2 UV pixels from SG-Lux, each one covered with a polarized filter from Night Optical, rotating them with a stepper motor with 224 points per turn, sampling coarsely the pattern of polarization with an angular step of 1.61 degrees. No optics was used, leading to an angle of vision of 120 degrees for each pixel. The onboard method comprises various processing stages, allowing it to be insensitive both to the UV index and to the clouds. Using a rotating mechanism limits the output refresh rate of our celestial compass to 0.25 Hz. Then we compared the optical heading measurements to a conventional GPS sensors working at 1 Hz. In A, you can see the selected 18.6 kilometers long journey in Marseille downtown, comprising straight boulevards to test both the celestial compass and the GPS to measure a steady heading in town. 2 boulevards, Michelet and Prado, are specifically interesting because they are straight and form a constant angle of 100 degrees. In B, from a statistical point of view, there is no significant difference between GPS data and the onboard method. However, the poor performances of the GPS-based methods must be treated with caution as signal failures occurred 85% of the time, whereas the optical heading was available 100% of time despite sometimes foliage between the sky and the celestial compass or buildings occluding a part of the sky. RMC and GGA data coming from GPS signals were used to compute the car heading, and the Hilbert and the Handbot method were used to compute the optical-based heading. In this table, we can observe that the Handbot method is the more reliable one to estimate the car heading with a root mean square error close to 0.55 degree. Moreover, You can observe on raw GPS data that it is unavailable about 85% of time. Here we show data in case of a sinuous road. When the road curvature is smooth, the curves follow the same variations. As a result, the celestial compass is a good candidate as a complementary heading measurement when the GPS is unavailable. In conclusion, firstly, a UV-sensitive celestial compass for the heading measurement in urban navigation is reliable. Secondly, it yields low root mean square error of 0.55 degree, which is the lowest root mean square error in comparison with other methods, GPS-based or Hilbert's methods. In turns and roundabouts, the onboard celestial compass does not work well because of its low output refresh rate of only 0.25 Hz. New developments are now focusing on using a photodiode array, each photodiode covered by a specific angle polarization in order to reach an output refresh rate of about 10 Hz. Thank you for your attention.